All right, ladies and gentlemen, welcome to another exciting day in the world of chemistry. The purpose of today's lecture is to allow you to name compounds containing polyatomic ions. In order to do today's lecture, you're going to need to have out a couple of different materials. So if you can please make sure that you have out on your desk your periodic table, as well as your common ion sheet and nomenclature flowchart. We'll go ahead and get started here. We're going to start by going back and quickly reviewing here what happens when you put a ternary acid in water. Recall these ternary acids contain ionic compounds. That is an ionic bond between a hydrogen ion and then a group of atoms that collectively share a charge. That is a polyatomic ion. And when these ionic species are placed into water, the water molecules, being polar, cause the ions to dissociate from one another, that is, to split apart. So if we take a look at this species here, H2SO4, the species H2SO4 is sulfuric acid. When sulfuric acid dissociates in water, it separates apart into, number one, a hydrogen ion, H positive, and number two, the hydrogen sulfate ion, HSO4 1 negative. And that HSO4 1 negative ion still has a hydrogen on it, which means it can further dissociate, producing another H positive ion, and now the SO4 2 negative ion in the solution. So when we want to look at this sequence of dissociations here, the acid which dissociated is the parent acid off of your ternary acid sheet here. Name of H2SO4 is sulfuric acid. And in order to name the ions which are derived from sulfuric acid again, we need to remember again those naming conventions we gave you, which was that ic acids produce 8 ions, and us acids produce ite ions. So recognizing again that the acid which produced our ions in solution was sulfuric acid, the ion derived from sulfuric acid would therefore be the sulfate ion. And then the species in the intermediate here that has the hydrogen still on it, the species HSO4 negative, would be named the hydrogen sulfate ion. And then again, looking at this sequential dissociation, the species produced in the solution are, number one, hydrogen ions, and number two, polyatomic ions, that is, groups of atoms that collectively share a charge. So looking at the rest of today's lecture, what we want to do is we want to be able to take those polyatomic ions which we're producing in the solution, and we want to be able to name compounds which contain those polyatomic ions. But in order to do that, I want to first take a look at a couple of kind of weird examples of polyatomic ions that go by different names than what we would expect from the ic to 8 ion, us to ite ion nomenclature that we've discussed. Alright, so now that we've seen where these polyatomic ions are derived from, the next thing we want to be able to do is to cut down a little bit of difficulty for you and make it so we don't have to go about doing that complete disassociation of the ternary acid in order to find the names of these ions. So if you can go ahead and take your common ion sheet, flip to the back side of the flowchart, and if you look in the upper right hand corner of that common ion sheet, you'll see that we have a list of the common polyatomic ions. The ions are arranged in this sheet by charge. So if you look in the upper right hand corner, the first box there contains all of the ions with a -1 charge. Down below that we have the -2 charge anions, and then we have the -3s and -4s as well. So if we want to find one of these common polyatomic ions, rather than going through and having to derive its formula or name each time, instead what we can just do is go ahead and look on that common ion sheet. So if you look for the first example here, we have the species SO4 2 negative. Looking on your common ion sheet on the right hand side, under the box with the -2 charged ions, you'll notice there that we have the sulfate ion listed as the name of that ion, which is the SO4 2 negative ion. So we can go ahead and name this species now as the sulfate ion, taking its name off of our sheet. So rather than going through now and determining the charges on the ions in order to find the name, all we have to do now is go about naming the species off of your sheet, which saves us a lot of time rather than having to write out that complete disassociation step by step in order to get to that name. So with that in mind, we can now go about taking a look at our second ion here. H3PO4 is an ion derived from phosphoric acid, but again, looking on your polyatomic ion sheet, we can determine the name of that species just by looking it up off of the -3 charged ions. So we find under the -3 charges, the ion PO4 3 negative is listed as the phosphate ion. Alright, if you'll have a look at the next species on our list here, the ion OH negative is a little bit different from the ones we've just looked at. The OH negative ion is not derived from a ternary acid. And the reason why we know that to be the case is because ternary acids contain hydrogen plus a nonmetal plus oxygen. The OH negative does not contain another atom besides oxygen or hydrogen, so therefore it can't be a ternary acid ion. But again, because we use this ion so often, we've listed its name for you on that common ion sheet. And again, under the OH negative 1 ion, if you look on your common ion sheet, you'll notice this listed as the hydroxide ion. So again, we can give the name here as hydroxide ion. A couple more on here just to have a look on your sheet again to familiarize yourselves. The borate ion. Borate ion, again, all of these are listed alphabetically. If you want to go ahead and have a look on your common ion sheets, the borate ion is listed under the -3 charged ions. That ion is BO3 with a -3 charge. So the formula of borate ion is listed as BO3 -3. And again, borate ion is derived from boric acid, which makes logical sense given that boric acid, H3BO3, when it completely disassociates and loses all three of its hydrogens, would produce that borate ion, BO3 3 negative. And then last but not least here, we have one more example, the nitrite ion. Please be very careful looking at the endings of these ion names because they tell you about where they are derived from. The nitrite ion is listed on your sheet under the -1 charges. Its formula is listed as NO2 -1. And again, nitrite ion, following our conventions, ite ions are derived from us acids. So the nitrite ion would be derived from the disassociation of nitrous acid. When HNO2, nitrous acid, disassociates to make an H positive ion, and the NO2, 1 negative ion. So again, using your common ion sheet can help cut down on the amount of time necessary to find the names of these species. Right, now that we've looked at how to use your common ion sheet in order to identify the formulas and names of commonly derived polyatomic ions, I want to take a look at a couple of special naming situations that we end up with. Remember, the names of these species have developed over time, and just like real languages, for some of these species, multiple different languages describe the exact same species. And so these ions here are an example of an older, slightly obsolete language, which we still see in use today in order to describe a couple of common ion species. So the first one I'm going to look at here is the ion HCO3 -1. Looking at that species, HCO3 -1, it becomes apparent that this is a ternary acid ion. The species HCO3 -1 would be derived from the dissociation of the ternary acid H2CO3, which is carbonic acid. Now that carbonic acid would undergo a dissociation in order to form the HCO3 negative ion when it splits apart in solution, producing hydrogen plus HCO3 negative, which could then further dissociate to make H positive and CO3 2 negative. Now, by our naming conventions, this acid here, which listed on your acid sheet is carbonic acid, would yield the ions HCO3 negative and CO3 2 negative. Ic acids make 8 ions, which would imply then that CO3 2 negative should be named the carbon-8 ion. So again, carbonate ion should be the name of CO3 2 negative. And following the conventions we discussed last class, HCO3 negative should be known as the hydrogen carbonate ion. And that hydrogen carbonate ion is the one that we want to discuss here. So by an older naming system here, the intermediate ion formed from the dissociation of a diprotic acid, that is an acid with two hydrogens on it, can also be known by applying the prefix bi. So a synonym of the hydrogen carbonate ion would also be the bicarbonate ion. So hydrogen carbonate and bicarbonate describe the exact same species, HCO3 1 negative. Following that same convention, the species HSO4 1 negative, a ternary acid ion derived from H2SO4, would either be known as, looking at the name of the acid, sulfuric acid. Ic acids make 8 ions. So the ions derived from sulfuric acid should be the sulfate ion, or the intermediate species, the hydrogen sulfate ion. And that hydrogen sulfate ion, following the conventions we just discussed, as the intermediate ion product derived from the dissociation of our diprotic acid, would also be known as the bisulfate ion. And one final look here again at another one of these special naming conventions. HSO3 negative would be derived from the ternary acid H2SO3. The parent acid of this family is sulfuric acid, which we just discussed. But we have one fewer oxygen on H2SO3, which would imply that the sulfuric acid would change to the name the sulfurous acid for H2SO3. And then our convention is that us acids make ite ions, which therefore implies that upon dissociation, we would end up forming H positive and HSO3 negative. Sulfurous acid would make the hydrogen sulfite ion. And another name for that hydrogen sulfide ion again would be the bisulfite ion. Now again, recognizing these kind of unique naming systems here that are still in use, you can still just use your common ion sheet. Again, looking at HSO3 negative 1 listed on your common ion sheet is listed as the bisulfite ion, the fourth species down there. So next we're going to look at one other special ion that you have to be on the lookout for. Besides those species bicarbonate, bisulfate, and bisulfite, another one to watch out for is the ion NH4 positive. NH4 positive is a special case in that it is the only polyatomic cation that we deal with normally in class. Again, polyatomic means a group of atoms that shares a charge, and the cation implies that that charge is positive. So the ammonium ion, NH4 positive, is again the only polyatomic cation which we will deal with here. Now, in order to name this species here, in the first example, NH4Cl, we're going to be naming our first compound which contains a polyatomic ion. Now the nice thing about this is even though these species tend to look nasty, the naming convention is very straightforward. All you have to do is name the cation, that's the positively charged species, and then name the anion, the negatively charged species. So if I look at the compound NH4Cl, within that compound is the species NH4 positive bonded to a Cl negative ion. And again, when we crisscross those charges, it will give me the formula NH4Cl. So to name the species, all you have to do is name the positively charged species, which in this case is NH4 positive, or ammonium, followed by name the negatively charged species. And in this case, we have the Cl negative ion, which you've already named many times before in compounds like NaCl, again, which is sodium chloride. those monoatomic ions, that is, the ions made up of only one atom, always end in IDE. So the species NH4Cl would be therefore ammonium chloride, NH4Cl. Looking at our next example here, we now have the ammonium ion, NH4 positive, now bonded to another polyatomic ion, NO3 negative. But again, the naming convention holds true. All we have to do is name the cation, which again was ammonium, and then name the polyatomic anion. And again, looking at that polyatomic anion, the species NO3 listed on your polyatomic ion sheet has a -1 charge. Looking it up under that sheet, you can find that the name of this species is the nitrate ion. So then the species NH4NO3 would therefore be known as ammonium nitrate. One final example here going the opposite direction, giving you the name, asking you for the formula. If I asked you for ammonium sulfide, the compound ammonium sulfide contains the ammonium ion again, which we said was NH4 positive, and the sulfide ion. Now the sulfide ion I can recognize as a monoatomic ion because it ends in IDE, just like our chloride, and this is a monoatomic ion of the element sulfur. Looking at your periodic tables, you find sulfur in group 6 of that periodic table. As a group 6 element with 6 valence electrons, it's small and electronegative. It will tend to pull electrons from other species in order to fill its octet. So that sulfide ion would therefore be a sulfur atom with a -2 charge, as the sulfur picks up 2 electrons to complete the octet. Once we recognize that we have now the formulas of the ions, all we now need to do is crisscross those formulas to make them into the compound. So crisscross the charge, make them into the opposite subscript. This gives me the compound. Be very careful here. I want a parentheses around the polyatomic species, NH4, 2, and then S1. So the compound ammonium sulfide is NH4, 2S. Alright, so now that we've looked at the ammonium ion, another special case that we have to be on the lookout for is another polyatomic ion here, which is the peroxide ion. Now the peroxide ion, as it turns out, is a polyatomic ion. It is a group of 2 oxygen atoms that collectively shares a -2 charge. So that peroxide ion is an O2, 2 negative ion. That is in contrast to the monoatomic oxide ion, which is simply an oxygen atom which has picked up 2 electrons to complete its valence shell. So the way to be on the lookout for this peroxide ion and to distinguish it from the oxide ion is to recognize that the peroxide ion is always bonded to a group 1A element, that is either hydrogen or an alkali metal, in a 2:2 ratio. So if I look at the species Na2O2, in order to make this compound, I would have combined together sodium ions, which have a +1 charge, with a group of O2, which collectively shares a -2 charge. And again, crisscrossing those charges gives me the formula Na2O2. Therefore, this species here is sodium peroxide. Now that's in contrast to the species Na2O. To make the species Na2O, I would have combined together a sodium ion with a +1 charge with an oxide ion with a -2 charge, and crisscrossing this time gives me the formula Na2 and then just O1. So again, this is a monoatomic ion, therefore the name of this species would be sodium oxide. So again, sodium peroxide with the -2 charge on the polyatomic O2 group, sodium oxide with the -2 charge on the monoatomic oxide ion. And again, watch out for those. You'll see them always bonded in a 2:2 ratio. And this is one of the only examples of a time when we do not reduce that 2:2 ratio to the smallest whole number ratio. So keep it as Na2O2, as the grouping O2 is actually a covalently bonded group stuck together. Alright, now that we have gone through and identified all the kind of weird outlier problem ions we might come across, we're now in a position where we can accomplish the kind of main goal of today, which is to be able to name a compound which contains polyatomic ions. Now, the conventions for naming these are actually relatively straightforward. All you have to do is name the cation and then name the anion. But the trick is, just like all of the other species you've dealt with up until this point, sometimes you have to watch out for weird situations in which those cations have multiple possible oxidation states, or the anions could have weirdly derived names. So we're going to go ahead and start off by looking at the first species there, which is FeCO3, and just jump right in using your nomenclature flowchart. So finding FeCO3 here is going to be a little bit tricky in that we are in a new position on the flowchart. Follow the flowchart along from the very first question. Is it an element? Answer is obviously no. Is it a binary compound made up of two types of atoms? Again, we have a no. Is it a ternary acid made up of hydrogen plus a nonmetal plus oxygen? Again, we would say no, there's no hydrogen present. And that brings us to the next question, which is it a metal plus a polyatomic ion? And the answer here would be yes. We have a metal, which in this case is iron, bonded to a polyatomic group, that is the CO3 group. So we're going to say yes, it is a metal plus a polyatomic ion. And the final question is, does the metal have multiple oxidation states? So just like before when we were doing the binary compounds, metal plus nonmetal, in this instance we're going to have to first identify the oxidation state of the metal by looking at what it's bonded to. So this time again we want to start with that polyatomic group. The CO3 group, looking on your common ion sheet, is listed under the ions with a -2 charge. And you see that listed as CO3 2 negative is called the carbonate ion. Now if we recognize that the compound overall must have a neutral charge, in order to have a neutral charge overall, that would imply that the iron ion must also therefore have a charge of +2. And then crisscrossing those charges would give me the compound Fe2 parentheses CO32, which would reduce down to a smallest whole number ratio of FeCO3. So at this point, we've identified the ions present in the species. Now all that remains is to name those ions. The ion Fe2 positive is either the iron 2 ion, or you could also call it the ferrous ion, applying our Latin naming system. And the group CO3 2 negative, off of your polyatomic ion sheet, was given the name carbonate. So FeCO3 would be either known as iron 2 carbonate, or an equally valid name would be ferrous carbonate. So iron 2 carbonate or ferrous carbonate. Let's look at the next example here. If we have the species K2Cr2O7, again, this is a metal plus a group of atoms that collectively shares a charge, so a metal plus a polyatomic ion. Again, with the metal plus polyatomic ion naming system, we need to first identify if the metal has multiple oxidation states. Finding potassium on your periodic tables, under group 1, the alkali metals, you'll note that the only possible oxidation state of potassium is +1. So the answer then would be no, the metal does not have multiple oxidation states. So naming this compound is as easy as name the metal and then name the polyatomic ion. So the metal here, potassium, and then the polyatomic ion here is Cr2O7. Again, looking it up on your polyatomic ion sheet, you'll find the Cr2O7 2 negative ion listed as the chromate, lied to you, listed as the dichromate ion. So this species is potassium dichromate. Alright, so we've now taken a couple of species and named them based upon their formulas. Now let's go the opposite direction. Take a name and give the formula. Again, these are ionic compounds, which would imply that we need to figure out the charges on those ions and then simply apply our crisscross method to find their formula. So to do with this next species here, barium nitrate. The barium ion is a monoatomic cation. Find barium formula on your periodic tables. It is a group 2 element in the alkaline earth metals, implying the charge on the barium ion must therefore be +2. And then the 8 ending of nitrate implies that this is a ternary acid ion on your polyatomic ion sheet. The nitrate ion, if you look that up, is listed as NO3 -1. And again, to form a neutral compound overall, I would need 2 groupings of -1 for each barium ion with a +2 charge. Therefore, crisscrossing those charges to make the compound gives me the formula Ba, and then again with a polyatomic ion in a parentheses to group it, Ba NO3 in parentheses 2. And one final species to look at here is potassium cyanide. This potassium cyanide is again a metal plus a polyatomic ion group. Finding potassium on the periodic table, you'll note it only has one possible oxidation state, which is +1, as it loses that one loosely held valence electron. And then the cyanide ion, looking on your common ion sheet, has the formula Cn1-. And again, crisscrossing these gives us the easy formula here, which is simply KCN, or potassium cyanide. And that's pretty much all there is to it. Name the cation, name the anion, paying attention to the special cases in which the cation might have multiple oxidation states, or that anion may be a polyatomic species.